Hello and welcome to Circuit Lab, practice number 11. How's everyone doing? I see we've got Mr. Dazzy on. Hello, Mr. Dazzy. Are you on? So while we're waiting for more to join, let's see who all else has joined. Still Mr. Dazzy. Okay. We'll wait for Mr. Dazzy to get back. Well, yes, as you've noticed, I'm in a different room, and that's why we had to move it. I'm actually visiting some friends in Ohio. So I'm in the great state of Ohio right now doing the podcast. I apologize for us having to do it 2 hours earlier. One of the things I'll check on is see if anyone's interested in doing it next week. I know it's the week right before Christmas. So if we wanted to take next week off or we want to take the next 2 weeks off I'm okay as well. But Mr. Dazzy, do you have any questions? So you might remember that this is Circuit Lab 11, which focuses on Kirchhoff's voltage laws, which focuses on specialty devices, dependent sources, superposition, and troubleshooting. Last week, we went over multiple sources, and we went over Kirchhoff's voltage and Kirchhoff's current laws. Okay. Are there any questions from last week? See, right now, Mr. Dazzy says there's no questions. Okay. And so this week, we're going to talk about some specialty devices. So we talk about switches, and just keeping in mind that a switch is any type of electrical component that we use to break an electrical circuit or divert it from one basic circuit to another. It'll have two states, open or closed. Open means that the circuit is broken, so it's open, and it's sometimes referred to as off. Closed is when the circuit is connected, so you have a short between two poles, and it's considered on. It can be toggle or momentary. A toggle is like a light switch. You flip the light switch, it stays on. You flip it down, it stays off. Momentary is like a push button for like a starter. You push it, and only while you push it is it closed or on. Okay. The key thing is to remember when you're doing a switch problem or a relay problem, and relays are just electrical switches, redraw the circuit for every configuration you want to test. So if you've got one switch, you'll draw it once with the circuit closed, and you draw it once with the circuit open. There are different types of switches. The main types are single pole, single throw, which are your normal light switch for like that just has on or off. Okay. A single pole double throw is a simple changeover switch, turns from one thing to another, but not both. So in other words, you can either go to this conductor or this conductor. So it's not on or off. It just goes between conductors. Now, when you get into the double poles are two switches, two poles. The switch itself is called a pole that are combined together, and they can either be a double pole single throw, where you either have them both go on and off, or you can have it where it goes between two different circuits with a double pole double throw. Like a double pole single throw switch might be like if you go to your circuit box and you look at a 220 amp or 220 volt breaker. Okay, what they do is they put two 110 volt breakers next to each other, and they tie the poles together, so it becomes a double pole single throw switch. Let's see if there are any questions. Okay. A fuse is a safety device that you put in series, usually with your power supply, such that if you start drawing too many amps, like you have a short or something, that'll actually burn out. Now, the neat part about a fuse is that they usually make it such as you can visibly see the fuse filament inside there, so you can tell visibly when it's burnt out or not burnt out. Okay. Also, they act really, really fast. So they're very good at preventing an overcurrent situation, preventing sparks, preventing fires, preventing somebody from getting electrocuted. The bad part, okay, is that once a fuse is burnt out, okay, in other words, once you exceed the maximum current rating through that particular fuse, it's burnt out and it has to be thrown away, and you have to replace it with a new fuse, okay, after you fix whatever was causing the problem. And usually somewhere on the fuse, it'll have however many amps it can handle, whether it's 2 amps, 3 amps, 4 amps, 10 amps, 40 amps, etc. A circuit breaker is like a switch that trips or goes to the open position, okay, whenever you exceed the current rating. So in other words, an 8 amp circuit breaker will trip if you go 8 amps or more. A 10 amp circuit breaker will trip if you go 10 amps or more. Now, what's really neat about these things is that when they trip, they go to open, shuts down the circuit, okay, you fix the problem, and then when you reset it, okay, you don't have to replace the circuit breaker. So it doesn't damage it. Now, one of the things, if you ever go to a breaker box and you think you fixed the problem, and then you flip it and you try to reset it and it automatically trips again, it means, hey, you have not fixed the problem. In other words, there is still a short somewhere. It could be a device that is shorted out. It could be that you've got too many plugs plugged into a single outlet or something like that. The other thing is that it's usually a little bit slower than a fuse. Okay. The other thing I would say is that, again, one of the best examples of a double pole switch is in a breaker box when you look at things for like your AC, your heat, your stove, your dryer, things that run on 220, they'll have the two poles linked together. And so that's a good example of one. Now, when we talk about dependent sources, those things are usually shown by a diamond shape instead of the circles that we saw with independent sources. And what that is that there's going to be some sort of mathematical equation by which either the voltage or the current relates to something else in the circuit. So it's usually relating it to a voltage or to another circuit or to another current somewhere. And so you see this quite often used for amplifiers, where we know the gain of the amplifier. So if the gain of the amplifier is 5 times the input voltage, then I would replace the amplifier with a dependent source that says it's 5 times the input voltage. Okay. Now, we give a lot of examples of these, and so we can still do KVLs, we can still do KCLs, okay? But what you can't do, okay, is you can't use superposition, okay? And so that's really important, okay? And you can't, where you take out dependent sources and whatever. So it usually involves a lot more heavy-duty algebra. There's some cases, and I gave a couple of examples that are pretty easy. Now, superposition, okay, is where you can solve with multiple different sources, independent sources in the same circuit. And what you do is that you do them one at a time, and then you add in the currents and the voltages together at the end. This does not work with dependent sources, and you can't use it with something that's got a square in it, like a power equation. So in other words, if you did a superposition and in one case it had 5 watts of power in this one resistor, in the other case it had 10 watts of power, you don't add them together and say it's going to have 15 watts of power. No, what you do is that you can say if I have 1 volt in one case and 2 volts in the other case, I have 3 volts. Or if I have 1 amp and I have 3 amps, then I have 4 amps, okay? And remember, when you replace the independent sources, you replace a independent voltage source with a short, and you replace an independent current source with an open. Okay, any more questions? Right now, it's just you and me, Mr. Dazzy. I tell you what, is there anything you want me to cover in particular? Did you want to talk about practice number 12? Okay. What's giving you the most problems right now? Okay, that's all right. Do you want me to just keep going through practice 11 slides? Okay. Well, I tell you what, let's just finish up practice 11 slides, okay? So an example of superposition is given in lots of the cases where you have 2 sources and they have to be independent sources. Just remember, don't try to use superposition when using dependent sources, and never try to use it to solve for power. Now, you can solve for power, but what you do is you solve for the voltage and the current first, and then you use power is equal to VI. Troubleshooting. Now, this is the Burleson method of troubleshooting. It is not always the best way. It's just the way that I do it. But I generally find that it works best if you first figure out if it works previously. Because if it worked previously, okay, if it worked before, something changed. the battery ran out of power, a component got loose, a component blew out, something like that. If it never worked, it could be a design error. Okay. It could be that everything is set up exactly right, but for one reason or another, there's a design error. Okay. So if it never worked, check the design for any flaws, including open and short circuits. So really go through and do a very quick analysis and look for open circuits, really. And then also look for short circuits. If it worked before, the most common problem is there's no power. So is it plugged in? It's the number one problem of all time. Are the batteries dead? Are the switches turned on? Okay, is it turned on? Is the fuse burnt out, or is the circuit breaker tripped? Okay, then the next most likely thing is one of the main components is out. Like, is your light bulb or your resistor, your motor, are they burnt out? Okay, now if it used to work and it passes all those tests, here's what I recommend. Draw the design such that it makes sense to you, label it. Try to figure out what the voltage and or resistance should be between nodes and write it all down on your drawing. Then you can go measure the voltage in parallel to all the elements with the power source on, just like it is running, and compare to your calculations. Okay. Now, you can measure resistance. Okay. But the power source needs to be removed or off. You can't, don't measure resistance with power on. Also, when you measure resistance, keep in mind that when I'm measuring resistance, I can't tell it where to measure it. So if I'm looking for one resistor, I need to actually usually remove that resistor from the device and measure it separately, because otherwise it'll find another path back because the rest of the circuit's all in parallel. Always check the obvious stuff. Is it plugged in? Is the battery not dead? Switch is on, wires connected, nothing loose. Keep in mind, if it's a series circuit, everything's going to go out at once. If it's a parallel circuit, only the burnt out one or the bad component will go out. When you're measuring the voltage, you're only going to get voltage if you have both current and resistance or an open circuit. Okay, so a short circuit will have both voltage and resistance equal to 0. An open circuit will have the resistance at overload, but it could have a voltage. So like if I've got a string of Christmas lights and I'm checking each one of the Christmas lights, I'm checking it with my voltmeter, and I find that I have 120 volts across this one bulb and it's 0 across all the rest of them, what that 120 volts across that one bulb, that's the one that's burnt out. It's got infinite resistance, and so I've got zero voltage across the rest. Now the voltage across a bunch of resistors in series with no circuit with no current will remain the same. So if you look at the example of the Christmas lights with the 6 volts, okay, now you'll notice that it's got a switch and it's got a fuse in series. So this is exactly how I would set up this diagram. So the fuse will protect my my light bulbs and my wires from an over current situation. All the lights were working but stopped suddenly. Okay, what are the obvious things to check? Well, honestly, the first thing I would check is the switch on or off. Okay, did I accidentally turn the switch off? The next thing I'm going to look at the fuse. Did the fuse burn out? Okay. The next thing I'll probably check is make sure I really do have 6 volts. Make sure you really do have power, because the battery could have gone dead. Okay. Now, if I look at this particular thing, since it's 6 volts and I've got 6 equal resistors or lamps in series, I know by voltage division that each one of those lamps should have about 1 volt of voltage. And so if I check the voltage across the switch, and the switch is the voltage across the switch is 0, that means, hey, good news, the switch is closed. If I check the voltage across the fuse and it is 0, Again, probably the fuse is okay. And I look at it, fuse, make sure it's all okay. I then make sure all the bulbs are pushed in correctly. And then I measure the voltage across L1, L2, L3, L4, L5, and L6. And what I find out is that the voltage is 0 for all of them because there's no current except at L5, and it's equal to the 6 volts. Well, then what that means is that the bulb burnt out at L5. Okay, now, if you look at the parallel circuit in slide 18, all the lights were working but stopped suddenly. Okay, now what do we check? Okay, well, since they all stopped and it was parallel, this is probably going to be either the battery, the switch, or the circuit breaker. Okay, that one of them has somehow tripped, is either open, or the battery is drained. Because the odds of all 6 of them burning out simultaneously is actually fairly low. So I measure the voltage, and I could find out that the voltage, the voltage is 6 volts at the battery, and it is nothing across the switch, and it's 6 volts at the circuit breaker, which means the circuit breaker has tripped. Okay. Now, if it was working properly and the switch was closed, the voltage across each light should be 6 volts because they're in parallel. Remember how to argue an illegal question. Make sure you've read the question. Be respectful. Ask for how to implement the question within the rules. Don't tell them they're wrong. Ask the event supervisor how to implement it. Reference a specific rule, and keep in mind that sometimes the rules have changed. Okay. You should be doing all the way through level 14 of the homework binder. Okay. And you should also be doing example tests. All right. So I think, Mr. Dazzy, are you good? Let's see if you're still with us. So if you have it from here, we will not schedule another one of these until, okay, when do you want to have the next one? To go over practice 12. We can go over 13 if you'd like, but I'm just saying, when do you want to have it? Do you want to have it in January? Because if I look at our calendar, next week, okay, so on the 23rd, so 12/23. Do you want me to go back to the normal time? Mr. Dazzy, did you want to go back to the normal time? Okay. I will set it up then. Listen, everybody take care. I hope you all had a good day. And if you need anything else, remember you can always email me. Take care.